Let's look at Lyapunov's second method. This is a method to understand the stability of a critical point. And it ideally comes from physical systems. So when we look at physical systems, let's think of like a ball on a roller coaster. And we know that the equilibrium is stable if the potential energy is at the local minimum. So in our roller coaster idea, if we are at the bottom of the roller coaster, wherever that is, or a local bottom, that is a stable equilibrium. While the equilibrium is unstable if the potential energy is at its maximum. So if we are on top of a mountain, it's true that there is an equilibrium in there, but any displacement will make us fall down because the potential energy is at its maximum. So maybe we can use this concept of potential energy and extract some information in the non-physical systems. Another thing about physical systems is that total energy is conserved. So when we're summing the potential energy and the kinetic energy, and maybe you're also talking about other types of energy like magnetism or whatever, if you sum all of that, the total energy of the system is conserved over time. So maybe we can also have a look in that direction and think about finding a quantity that will tell us what is conserved over time in our specific system. So let's look at an example. We're going to relate the pendulum, undamped at the beginning, damped after, with conservation of energy. So we have the undamped pendulum with a mass. The angle between the vertical and the pendulum is the thing we're checking, and it's changing over time. So the second derivative of this angle multiplied by the mass plus a constant given by the mass times the gravity divided by the length of our pendulum arm multiplied by the sine of the angle. We want all of that to be equal to 0 at all times. So we can rewrite it as a system because that's what we have been doing lately. We take higher order ODEs and turn them into systems of ODEs of first order. So the system is x dot equals y and y dot equals minus g over L sine of x. We have simplified away with the mass, where x is the angle we have been dealing with and y is the derivative over time of the angle. In this case, because we know the physical system that we're coming from, we can talk about potential energy, that is the height at which we are, up to a constant. We can throw away the constant and only talk about what we can change of the potential energy. And we can talk about the kinetic energy that depends on how fast we're traveling. So in this case, the potential energy is m times g times L, that is the length of our pendulum, times 1 minus cos x. And the kinetic energy is 1/2 times m times L squared times theta dot squared, or y squared. So the total energy is the sum of these two when we write them with respect to x and y. And what we expect is the total energy to be conserved over time. Because this is undamped, so there is no dispersion of energy, no new energy coming in. So we expect the total energy to be conserved over time. Over time means that if we choose x and y to be functions of time that satisfy our ODE system, then we expect v of x that changes over time and y that changes over time to be conserved over time. So let's try to check this. We want to compute the energy change over time. But the energy depends on the position and the velocity. So what we're thinking about is the energy depending on x of t and y of t, where x of t and y of t are the solution of our ODE system. And we take the derivative with respect to time of v that depends on x that depends on t, and of y that depends on t. So this becomes the derivative of v with respect to x times the derivative of x with respect to t, plus the derivative of v with respect to y, times the derivative of y with respect to t. And we can compute this. Well, we keep x dot and y dot, and we compute the partial derivatives of v. We know how to do that. So we retrieve mgl sine of x times x dot plus ml squared y dot. But because we know that x and y are solutions of our ODE system, then we know what x dot and y dot are as a function of x and y. So we replace that in, And we notice that it simplifies and goes to 0. So as we have expected before, the energy change over time is equal to 0. So the energy is conserved. That means that trajectories are following contour lines of V. Notice that this we know, the conservation of energy is known without ever solving the system. We have constructed a function V of x and y that doesn't depend strictly on our ODE system, but because we know that that is conserved over time, then we have information about the solutions. This is why this is called a direct method. It doesn't need to first compute the solutions and then have some information. We can immediately have some information on the results. So what we want to know is, how can we use this information about the energy to deduce information about the critical point? The idea is that if we're taking x1 and y1 close enough to the stable critical point, the fact that solutions need to maintain the energy will give us some information about the shape of the solution. So we have one point that has x1 and y1, and we want to check through V all other points that are possibly reachable from x1, y1. What does it mean by reachable? It means that there could be a trajectory connecting them. That means we want to find all the x's and y's such that the energy at x and y is equal to the energy as x1 and y1. Because if the energy is equal, then there might be, it's not sure, but there might be a contour line. And if there is a contour line, there might be a trajectory. So now we're going to look for V of x and y. And we expect x and y to be close enough to 0, 0, so we can approximate the cos of x by 1 minus x squared divided by 2 plus, well, the full Taylor series would also involve x to the 4th divided 4 factorial and x to the 6th divided 6 factorial and so on. But because x is very small, we claim that the most important terms are the first two terms of our Taylor series. So we drop the others. So we're approximating our energy function at x and y by this formula mg times L times x squared divided by 2 plus 1/2 mL squared y squared. And we want the energy at x and y to be equal to the energy at x1, y1. In order for that to solve, to be true, then we have this new formula in which x squared times a constant plus y squared times another constant needs to be equal to 1. Therefore, we need x and y to belong to an ellipse that is passing by x1 and y1. What does it tell us? It tells us that if we're sticking at the same energy level, we need to be at an ellipse around our critical point. What does it tell us? That at most, trajectories need to stick there. There might be the weird case, shouldn't, but there could be, in which trajectories stop at some point so they don't go along the full contour line. But in general, we're not going to see that odd case. What happens if we add damping? So we add to y dot a negative term depending on y, minus c divided ml times y. If we have the same energy function as before, so the v as defined before, we find that the derivative over t of v, that means we consider v as a function of x, function of t, and v as a function of y, function of t, and we derive with respect to time, then we have that the derivative of v with respect to time is minus c L y squared. And that is negative because we expect c and L to be positive and y squared is always positive. So what we know now is that v, the energy over time, needs to be constantly decreasing over time. That means that if you're thinking of all the ellipses around our critical point that are like the contour lines of v, the fact that dv over dt is negative means you're going down through the contour lines, maybe very slowly. So the trajectories must approach the critical points with minimum energy. except maybe for y equal to 0, in which case dv over dt is actually equal to 0. So in those 2 points where y is equal to 0, where you're considering the contours, then you're not going downwards. But in all the others, you're going towards the critical point.